Hi everyone, welcome to our lecture on constitutional isomers. This is part 2 of alkanes. On the notes here we have 3 structures of alkanes, and we want to determine the chemical formula. What I did was I highlighted the carbons, so we have 6 carbons in each of these. If you go through and find out how many hydrogens you have in each, you'll see that they all have 14 hydrogens. So the formula is C6H14 for all 3 of these. Now, how are they different from each other? So if you look at the structure of these, the way that they're connected, the way that the carbons are connected is different. So here you have a straight chain hexane, whereas here you have a methylpentane, and the methyl's in different positions. So these are when you have constitutional isomers. I would define constitutional isomers as 2 molecules that have the same chemical formula but different connectivity. Connectivity being how the carbons are connected. So one hint for that is sometimes it's hard to tell. So I usually name it, and I tell by saying, oh, this is N-hexane, this is 2-methylpentane, and 3-methylpentane. So that's a really easy way to tell. Go ahead and take a minute and see if you can determine which of these are constitutional isomers of hexane. Alright guys, we're back, and this is my cat Ginger. She wants to do this too. So the first couple of these, you notice the connectivity is the same as hexane, just straight chain hexane. So we would call those conformational isomers. That is, you can see the rotation of the carbon bond, like right here. It sort of rotates up. And this is another different rotation of hexane, but it's basically connected the same way this one is, just one after another. With the constitutional, we see that right here. There's 6 carbons here, and they're all in a different kind of branching pattern. So this is definitely a constitutional isomer. Again, if you use my trick, which is to name it, it's a 2,3-dimethyl butane, right? So this is definitely a constitutional isomer. This is conformational again due to rotation. You could just rotate it to any of these, and so they're conformers of each other, which is what we covered last time. These two here actually are different. They're not even C6H14, so these are not isomers of any of these. If you notice the ring, you'd have to take a chain of hexane, remove 2 hydrogens to hook them up. And if you tried to make a pi bond, you'd have to again remove 2 hydrogens to have space for a pi bond. So these are neither kind of isomer because they don't even have the same formula. So in this next part, we're going to look at the relationship of carbons to hydrogens. If we have pentane, so that's 1, 2, 3, 4, 5. You could count that to get the chemical formula, or you could plug into this really nice little equation, CnH2n plus 2. That's for alkanes. So let's use that. So let's use this to calculate C5. If n is 5, H2n, or 2 times 5 plus 2, is 12. And then you can confirm that by counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay? That's really handy because then you know what the formula will be for any number. Let's say 10 carbons. You don't have to count them all. You can just say C10H20 plus 2, 22. All right, so it's a really nice way to get a formula really quickly. Because remember, it's not just the straight chain, but it could be any branched version, and it's nice just to know, oh, it's an alkane, just related to the number of carbons. For every ring or pi bond, remember we talked about 2 hydrogens removed to hook the chain together or to make a pi bond. So this is considered unsaturation. Unsaturation means the removing of hydrogens. Here we didn't remove any hydrogens. We don't have any pi bonds or rings. So in alkanes, we consider those to be saturated. Alkanes are saturated. So in all of these structures here, these guys over here are saturated. These have unsaturation. So you guys have probably heard about saturated and unsaturated fats. And so saturated means that it's no double bonds or rings. And unsaturated fatty acids have pi bonds, sometimes several pi bonds in them. So you have monounsaturated, diunsaturated, polyunsaturated. So it tells you how many, relatively how many pi bonds there could be. What would be the general formula for a cyclic alkane or alkene? So if you have 2 hydrogens removed to make a cyclic alkane or 2 hydrogens removed to make an alkene, we know that from the saturated alkenes, CnH2n plus 2, if we remove 2 hydrogens, then we end up with CnH2n. All right? So if we look at these structures here, C6, count up how many hydrogens you have. So we have 2 on each of these, so that makes 12. And same here, if you 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So both of these are C6H12. So they are not even possibly isomers of these guys. So this equation does fit because I had Cn, which is 6, n equals 6, H equals 12. So we call each ring or each pi bond a degree of unsaturation. So if you look at benzene, it's got 1 ring and 3 pi bonds. So that's a total of 4 degrees of unsaturation. So go through each of these and determine how many degrees of unsaturation do you see in that molecule. Alright guys, so in the second one I get 3 degrees of unsaturation due to these 3 pi bonds, 2 rings here, so 2, 1 pi bond here, and 2 pi bonds here. So a little summary is 1 ring is 1 degree of unsaturation. When you see a double bond, think 1 degree of unsaturation. And when you see a triple bond, think 2 degrees of unsaturation. Now I'm going to show you how to go in reverse. If you had a chemical formula, without drawing the molecule, could you tell how many degrees of unsaturation it might have? And this is really handy because I might say C6H12, draw me some of those, draw me some isomers of those. And you might start with a straight chain and then draw all these saturated ones before you realize, oh, they all have 14 hydrogens. I didn't account for the fact that there's a degree of unsaturation there. So it really helps to know. Well, one easy way for solving that is to think about the saturated version, C6H14. And if I tell you to draw C6H12, you should notice, oh, 2 hydrogens have been removed. So that's 1 degree of unsaturation. So you should start drawing molecules that are cyclic or have 1 pi bond. Or maybe I gave you C6H10. So now you know 14 minus 10 is 4 hydrogens removed. That's 2 degrees of unsaturation because 2 hydrogens for every degree of unsaturation. So that's one easy way, and that's easy if you have just carbons and hydrogens. But if you have oxygens and nitrogens and halogens, it can become different. So one thing you could do is just draw a hypothetical molecule with all those atoms in it, and then count how many empty spaces you have. So when we have C6H12, go ahead and just draw 6 carbons and put in 6 hydrogens, doesn't matter where, just so the valences work out, everything's neutral, honk rule, whatever you want to use. And then find out how many spaces are left, and those represent the hydrogens that were removed for the unsaturation. So we definitely know, because these are empty spaces, the hydrogens were removed. This is not saturated. It's definitely unsaturated. To find out how unsaturated it is, we use the number of spaces divided by 2, because number of spaces are the hydrogens that would have been there if it was saturated. And then for every 2 removed, that's a degree of unsaturation, like a ring or pi bond. So count these up, 2, 4, 6, 8. Okay, so 8 degrees, or 8 numbers, so 8 spaces divided by 2 is 4 degrees of unsaturation. What this means is I could have 4 rings, or I could have 4 pi bonds, or I could have 2 triple bonds, for example, which are 2 pi bonds each. Or you could have some combination, like 3 rings and 1 pi bond, or the reverse, 1 ring and 3 pi bonds. So we had actually gone through one of these before. It was benzene, which has a ring and 3 pi bonds, so that's 4 degrees of unsaturation. So think of another structure you could have. All right, guys, so the answers will vary. There's so many possibilities here. I just drew a straight chain of 6 and then put in 2 pi bonds here and 1 pi bond there. That's 3 degrees of unsaturation, and then I can add 1 more there. And I made this straight because, remember, this is sp, hybridized for triple bond. All right, guys, I'd like you to take what we learned just now and apply it to these questions right here. And then we'll come back and we'll talk about 11 together. All right, guys, so on this one, number 9, I hypothetically drew a molecule with 7 carbons and 8 hydrogens, and then it was a little tricky with the nitrogens and oxygens because I want to make sure they have hydrogens in order to fulfill an octet, and I don't want to draw a double bond O because that's introducing unsaturation. So I'm going to make sure this is an actual hypothetical molecule that could exist. And then looking at the spaces here, I have 8 spaces divided by 2 is 4 degrees of unsaturation. So going through each of these molecules, how many degrees of unsaturation are there? So the first one has 4 degrees of unsaturation because it has a ring and 3 double bonds. This one has 2 rings and 2 pi bonds, so that's also 4 degrees of unsaturation. This is 2 rings and 2 pi bonds. And this one is a ring and 2, 3, 4. So this is 5 degrees of unsaturation. 2, 3, 4, and then the ring is 5. So that one doesn't fit. Going to the next one, number 10, first I figured out how many degrees of unsaturation I would have. And then I went about using that to figure out how, what kind of isomers could be possible. So I started with just a straight chain of 6 carbons, and then thinking about ways to use the oxygens with unsaturation, and then pi bonds here as well, 4 pi bonds, so that's 4 degrees of unsaturation. And these as well with a ring. And so I just tried to be creative and come up with ways of doing that. And all you have to do is go through and count how many atoms you have, right? So you go through and make sure you only have 4 hydrogens for each of these. All right, guys, so with isomers so far, we've covered 2 types. The first type isn't really isomer in the sense that it's the same molecule. So I have pictures of Ginger here. Ginger could be sitting down, or she could be standing up with her legs up in the, sort of her tail, when you pet them in the back, their rear end goes up. So she could have different conformations, but she's still the same cat. But with constitutional isomers, we're talking about different molecules. They have the same pieces and they have the same parts, but they're arranged differently. So here's Ginger walking around, but here's some other cat that had a deformity and has a tail sticking out of its head, or its legs and arms aren't in the right places. So the connectivity is what makes them different, and they're going to have different properties. So with this problem, I want you to use those terms. So comparing the 2 of these 4 molecules, are they conformations of each other? So are they conformers, meaning the same molecule but different rotations? Or are they constitutional isomers and the connectivity is different? Or are they not even the same chemical formula? Go ahead and give these a try. Okay, guys, we're back, and 1 and 2 are conformers of each other. You can see that there's been a rotation, so this methyl group sticking up is now sticking down. 2 and 3 are constitutional because their connectivity is different. We have straight chain versus putting a methyl group somewhere else. Here, number 4, these are not the same chemical formula because we have a degree of unsaturation, which makes the chemical formulas different. So they're not isomers. All right, have fun practicing. Keep practicing the degrees of unsaturation, drawing isomers with a certain chemical formula, and identifying what type of isomer you have, whether they're conformers of each other or constitutional isomers, or maybe they don't even have the same formula. Good luck, you guys.